Before we can understand CORS, we have to go back to its foundation, a core security principle of the web called the Same Origin Policy, or SOP. For decades, this policy has been the silent guardian of your browsing experience, protecting your sensitive data on one website from being stolen by another. Think of it as a strict security guard for every browser tab. To see why this guard is so important, let's define what it's protecting.
So, what exactly does the Same Origin Policy consider an origin? It's not just the domain name. An origin is a precise combination of three distinct parts: the protocol, the host, and the port. If even one of these three components differs between two URLs, the browser considers them to be from different origins. This strictness is the key to its security. Let's break down these three components.
Now that we know the three parts of an origin, let's see this in practice. Imagine our web page is at https://app.example.com. A request to an API at the exact same URL is, of course, same origin. But a request to http://app.example.com fails because the protocol is different. A request to https://api.example.com fails because the host is different. And a request to https://app.example.com:8080 fails because the port is different. This is the Same Origin Policy in action.
This strict security is fantastic, but it presents a major challenge for the modern web. Today's applications are rarely self-contained. We constantly need to fetch data from third-party APIs, load fonts from a content delivery network, or communicate between different microservices hosted on subdomains. By default, the Same Origin Policy would block all of these legitimate requests. This is the exact problem that CORS was created to solve.
And so, we arrive at the solution: Cross-Origin Resource Sharing, or CORS. CORS isn't about disabling the Same Origin Policy, it's about creating a safe and controlled set of exceptions to it. It's a mechanism that allows a server to explicitly tell the browser, "It's okay, I trust this other origin. You can let it access my resources." This is all handled through a conversation using standard HTTP headers. Let's see how that conversation begins.
The CORS conversation splits into two main paths, depending on the type of request: simple requests and pre-flighted requests. A simple request is considered safe enough to send directly, while a pre-flighted request is potentially more complex and requires the browser to ask for permission first. The browser automatically determines which path to take based on the request's method, headers, and content type. We'll start by exploring the simpler path. For a request to be considered simple, it must meet a strict set of criteria. It must use an HTTP method of GET, HEAD, or POST. Furthermore, it can only include a handful of specific headers, and if it's a POST request, its content type header must be one of three simple types. If a request meets all these conditions, the browser sends it directly, but with one special addition. Let's see what that is. That special addition is the origin request header. Whenever a browser makes a cross-origin request, whether simple or not, it automatically attaches this header. The origin header tells the server the protocol, host, and port of the page that initiated the request. It's the browser's way of introducing itself, saying, "Hello, server, this request is coming from https://myapp.com. Are you willing to share your resources with me?" Now, the ball is in the server's court. Upon receiving the request and seeing the origin header, the server checks its own CORS configuration. If the server is configured to allow that specific origin, it will add a crucial header to its response: access control allow origin. The value of this header tells the browser which origins are permitted. It's the server's explicit permission slip. Let's see what happens when the browser receives this response. When the browser receives the response, it performs a critical check. It compares the origin it originally sent with the access control allow origin value it received from the server. If they match, success! The browser knows the server has granted permission, and it allows your web page's JavaScript to access the response data. The connection is made, and your application works as expected. But what if the server is not configured to trust the requesting origin? In this case, the server might not include the access control allow origin header at all, or it might send back a value that doesn't match the browser's origin. When the browser sees this mismatch, it enforces the same origin policy. It blocks the response from reaching your JavaScript code and logs that infamous CORS error in the console. This is the security feature in action, preventing unauthorized access.
Simple requests cover many basic cases, but modern applications often need more. What if you need to use a put or delete method, or send a custom authentication header, or post application/JSON data? These actions are considered more complex or potentially dangerous. For these, the browser insists on an extra layer of security, the preflight request. A preflight request is like a reconnaissance mission. Before sending the actual, potentially data-altering request, the browser sends a preliminary options request to the server. This options request doesn't contain any of the actual data. Instead, it asks the server for permission. Hey, I'm about to send a put request from this origin with a custom XAuth token header. Are you okay with that? This pre-check ensures the server is aware and approves before anything significant happens.
This options preflight request carries its own special set of headers to describe the actual request that wants to follow. The access control request method header specifies the HTTP method that will be used, like put. The access control request headers header lists any custom headers the client wants to include, such as authorization. Together with the standard origin header, these give the server a complete picture of the intended request.
In response to the preflight options request, the server sends back its own set of access control headers, effectively laying out its rules. The access control allow methods header lists all the HTTP methods it allows from that origin. The access control allow headers header lists all the custom headers it will accept. If the server approves the request, it will also include the familiar access control allow origin header.
To improve performance, a server can also include the access control -max age header in its preflight response. This header tells the browser how long, in seconds, it can cache the results of this preflight check. For example, a value of 86,400 means the browser can skip the preflight options request for any subsequent complex requests to the same URL for the next 24 hours, proceeding directly to the actual request. This significantly reduces latency. So let's put it all together. If the preflight response from the server successfully validates the browser's intended method and headers, the preflight succeeds. The browser then immediately sends the actual request, the put request with its JSON payload, for example. Because the server has already pre-approved the operation, this second request will be processed and its response will be delivered back to your application. This two-step dance ensures maximum security. However, if the server's preflight response does not permit the intended method or headers, the preflight fails. The browser sees that it does not have permission and immediately stops the entire operation. Crucially, the actual request, the one with your data, is never sent. The browser simply logs a CORS error in the console, protecting the server from receiving an unauthorized request in the first place. This is a vital security stopgap. Let's move to an advanced topic, credentials. By default, browsers do not include credentials like cookies, authentication headers, or TLS client certificates in cross-origin requests. To include them, you must explicitly opt in on both the client and the server. In your client-side code, you must set the credentials option to include. On the server, you must respond with a header access control allow credentials true. Both sides must agree.
There's a critical security rule when working with credentials. A server cannot respond with both access control allow credentials true and access control allow origin star. The wildcard origin is considered too permissive to be combined with trusted credentials. If a server needs to allow credentials, it must specify a single explicit origin in the access control allow origin header. This prevents sensitive cookie data from being sent to any arbitrary site.
Finally, let's talk about debugging. Your number one tool for solving CORS issues is your browser's developer tools. The Console tab will give you a descriptive error message explaining why the request was blocked. Was the access control allow origin header missing? Did a preflight check fail? The error message often holds the key. Always start your debugging journey here.
For a deeper dive, the Network tab is indispensable. Here, you can inspect the exact headers for every request and response. Select the failed request. you may need to look for the Options Preflight Request first. Check the request headers to ensure the origin is what you expect. Then examine the response headers to see exactly what the server sent back. This is where you'll spot a missing or mismatched Access Control Allow Origin header.
And there you have it. We've journeyed from the foundational same origin policy, understood its limitations in the modern web, and explored how CORS provides a secure solution through simple and pre-flighted requests. You now know how the browser and server use HTTP headers to negotiate access, how to handle credentials, and how to debug issues when they arise. CORS is not an obstacle. It's a fundamental pillar of web security that enables the powerful, interconnected applications we build every day.